Hi everyone, my name's Adam. Welcome back to part 9 of my video series on creating a float controller using X-Plane and LabVIEW. In this video, we're going to continue looking at some integral related effects, specifically integral windup. This is often ignored in theoretical control systems material, which assumes that our system is operating in a controllable region around a set point, but it's a very real effect in real-world systems. In this video, we're going to take a look at a few methods that people might try and use to control windup and see what the pros and cons of each method are. Let's get into it. Let's talk about another problem that can occur with integral controllers, and it's similar to overshoot but different, and that problem is called integral windup. So integral windup occurs when we create a set point that the aircraft can't reach in its current set of conditions. We set it a pitch that it can't achieve or a speed that it can't achieve, and what the problem is that it will just continue to accumulate and accumulate. It's trying to feed in more and more control input to try and get the aircraft to where we've told it we want it to be, but the control inputs, additional control inputs aren't enough to get the aircraft there. The aircraft just physically can't get to those conditions. And a really easy way to demonstrate this is to start off with an aircraft on the ground, like this. We set our integral gain to its normal value. So yeah, we're going to try and take off. So we're going to set pitch to a very modest value. Say we want 5 degrees of pitch to take off with. And with only proportional control, that's just fine. The aircraft dials in some amount of elevator, about half of its maximum elevator. And if we started our takeoff roll now, the aircraft would take off just fine. The problem is, if we have our integral control always enabled, and ideally at some point we don't want to have to manually control it, we'd like it to look after itself. So if it's automatically enabled, watch what happens. So you can see immediately the integral starts to build, the control system, the control outputs go to maximum, so it's sitting there now with maximum elevator deflection, and the integral is continuing to build, and it will continue to build until one of a few things occur that we'll talk about in a minute. So let me demonstrate what happens now if we try and take off with that integral enabled right from the start. Turn on auto scaling just so you can see that the integral is continuing to grow. And if you recall from before, a typical value for our integral might be plus 400, and so it's growing massively. So let's see what happens now. We add some speed, release brakes, elevator is at maximum deflection, and notice that our integral is going to continue to climb until our pitch is more than the 5 degrees that we set. So I just said that when the aircraft went past 5 degrees of pitch, the integral would start to unwind. But if you watch the behavior of the aircraft, and if you watch our integral chart on the right, you'll see that in fact that's not what's happening. I'm going to let this run, and I just want you to look at that waveform chart on the right hand side of the integral behavior and think back to what we did in the last video and see if you can work out what's actually going on there. So the changes we made in the last section to when we enable and disable our integral actually made that behavior much worse than it should have been, because even when we pitched up way beyond our set point, we didn't start reducing the integral until the rate of change of pitch dropped to 0, which was basically when it was stalling. So I'll just go in and fix that quickly temporarily. Alright, so let's repeat that same test. Heading hold on, we turn on our integral and it climbs massively and continues to do so, even though our pitch set point is quite modest. And then we'll start our takeoff run and see what happens. So once again, the aircraft's trying to pitch up as hard as it can. And that's actually not as bad as I expected. But one of the things about this integral windup is that depending on how long you're sitting on the ground there before you take off, that can be much, much worse. Let's just demonstrate that again. So we can see here we're at a pretty huge value, but this will just keep going. You know, this value is a 32-bit integer, I think, in this case, so it's going to get really, really huge before it runs out of range. So let's try take off again now. We'll do the same thing. We don't like to have characteristics of the system like this that vary depending on time, you know, depending on what we've done prior to that point in time. We would ideally want the system to respond the same all the time. So we can see now that, you know, that integral is coming down, but it's still up at 40,000, and we want it to be down near 400 somewhere. So this is not going to fly how we would like it to fly. You know, in this case, just by virtue of the handling characteristics of the aircraft and whatever else, it will actually fly its way out of this eventually. But it's going to do this horrible, you know, porpoising sort of motion, terrifying everyone involved for a significant period of time before it actually gets to where it needs to be. The other thing that it could do, which would be interesting, is that if it got enough speed up, it would actually go past 90 degrees of pitch and pitch over to being upside down. I don't think it's going to do that. It looks like it's okay, so it's actually recovered there. So that's not, you know, it's not terrible. And if that was a model aircraft or, you know, UAV or something, it's not desirable, but it's not the end of the world. If that was a passenger aircraft, that's probably pretty terrible behavior. You know, it's the sort of thing that might be okay if it happened during developmental testing on a UAV, but on anything else, you know, on an operational UAV or on any sort of real aircraft, that would be completely unacceptable behavior. So we need to work out how we can stop that from happening. Here's another example of integral windup. We've got our C-130 sitting on the runway here, and what we'd like to do is just gently taxi it down the runway. We want to do a taxi test, a ground handling test of some sort. So we just want to go down the runway at 10 knots. So I've set my set point to 10 knots. We've got the brakes applied. We're just waiting there for that other aircraft to get out of the way. But the whole time we've been sitting here with the brakes applied, the integral's winding up. So you can see here, the integral output from our control is up around 1500, bearing in mind that actual maximum values are between -1 and 1. So let's see what happens now if we release the brakes. Remembering that what we want to see is just a gentle 10-knot taxi down the runway. It's not ideal. So obviously, because of this integral wind-up, the aircraft's going to keep applying maximum throttle until this integral comes all the way back down to below 1. And that's going to be a long time. Like if that integral's been sitting there winding up for 15 minutes at 10 knots, then at 150 knots, it's still going to take a couple of minutes for that integral to unwind itself again. And by that time, we're well and truly off the runway, we're in the air, we're doing all sorts of things that we didn't want to be doing. Obviously this is not going to happen probably in a real aircraft, but it's the sort of thing that can very easily happen with a UAV of some sort. You get it set up at the field, you turn it on, the flight controller's sitting there, the integrator's winding up, and then you enable the ESC and the aircraft just takes off. And it's going to be several minutes before you can bring the speed back under control. So this thing should fly along now. I'll let it run and we'll see how long it takes to get back to a controlled speed. And so the other danger with this, particularly in the UAV case, the aircraft takes off and it's flying around at full throttle, and so you take control of it, you're trying to land. At some point this integral is going to drop, and all of a sudden the thing is going to try and slow itself down to 10 knots, and you're probably not going to realize by that point what's going on, and it's just going to make for a very bad day. So we need to stop this from happening. I'll let this run, we'll just see how it goes, but then we'll talk about what we can do to stop this from happening. Okay, the integral's dropping now, and you can see it's just dropped all the way through 0. And so now our throttles have dropped to 0. And it's now going to stay there for quite a while. So because we're going so much faster than our set speed, the integral is now going to wind up in the opposite direction. So I'm going to go through a few different ways that we can try and control integral windup. And I'm going to say right from the outset that not all of these are good ways to achieve this, but they are ways that I've tried in the past, or I've seen other people try it in the past, and they might be ways that occur to you, and you probably won't find some of them in a theory textbook, but I think it's good to explore them and look at what the effect is that they actually have and whether or not they're right for a particular situation. So the first one that we're going to look at, and we've already looked at it a bit, is we can control the conditions under which the integral is enabled. So we already did this in the prior video when we were looking at controlling integral overshoot, where we disabled the integral based on either our error value or the rate of change of our process variable. And the whole idea of that was to not be accumulating large amounts of integral when we were a long way from our set point. So similarly, in this case, we can disable the integral if we know that we're in conditions where the aircraft isn't going to be able to reach its set point. So if we're on the ground, for instance, we know that we're not likely to be able to achieve any given pitch set point because the pitch angle of the aircraft is just controlled by it sitting on its landing gear. Similarly for roll, so we might want to disable integral completely while we're on the ground. But we need to think about whether we want it always disabled when we're on the ground or just sometimes disabled. So for example, our pitch integrator, we don't want that to be enabled where the aircraft is now, where it's just sitting here idling on the runway. You know, we're not going to be able to achieve a given pitch angle, so there's no point having the integrator enabled. However, once we start our takeoff roll, maybe, depending on the characteristics of our aircraft and our control system, maybe we do want the integrator to start working so that we can achieve our takeoff pitch angle, whatever that might be. So how do we determine that transition point? You know, it's not simply a case of deciding are we on the ground or not. We need to look at are we on the ground and are we below or above some speed, for example. Now this will also apply for something like heading hold. So we probably want our heading hold to have some integral ability while it's on the ground so that it keeps us tracking straight down the runway, particularly later on once we start introducing wind and other disturbances. But as with all our other integrals, we don't want it winding up while the aircraft's stationary. So the simplest way that we can do this is to enable and disable our integrals based on a speed threshold. If we pick a speed that's below the stall speed of the aircraft, we can assume, and we need to think carefully about whether it's a valid assumption, but for the moment we'll assume that if we're below that speed, that A, we're on the ground, and B, we don't want any integral control. So that's what I've done here in the block diagram. I've grabbed our airspeed and said that if our airspeed is above 40 knots, then we feed this enable signal, this Boolean enable signal into our single axis controller. And if we go over to the controller, all I've done is added that into this AND block with the existing enable signal. It's a bit of a hacky way to do it, but it was the quickest way to do it given that these signals are tied up in this cluster. So the reason I've selected 40 is because I believe the rotation speed for our Cessna 172, the point at which it will start to get airborne, is around 60 knots. Might even be a bit below that, so 40 seems like a good point to start enabling our integrals. Now that's not necessarily true, but it's just a number I've picked. Maybe it's not going to be the same for all our integrals. Our heading hold we might want to enable sooner, sort of as soon as we start moving. But we can determine that through some trial and error or some testing. The other important thing to think about here, and it's particularly important with low speed aircraft, and this Cessna probably counts, but once you get into things like UAVs and quadcopters where your airspeed can be very close to the wind speed, it's important to know whether you're talking about ground speed or airspeed. So here we're looking at airspeed and we've got no wind, so airspeed and ground speed at the moment are the same thing, but they're not normally going to be the same thing. So this is saying if our airspeed, our speed through the air, is greater than 40 knots, then we'll enable that integral. Now what that means is that if we're taxiing, say, at 20 knots and we've got a 20 knot headwind, that integral is going to enable itself even though we're on the ground. And that might not be what we want, particularly if it's, say, our pitch integrator. So maybe you say, oh well, that's easy, we'll just choose ground speed instead. But then you have the opposite problem. So imagine our Cessna is flying a circuit, and imagine for a moment that there is a 30-knot headwind blowing down the runway. Now that's pretty strong, but imagine it's a consistent, non-changing wind, so we can land into that. And imagine we're approaching at 65 knots. So we're flying along 65 knots. Our integral's enabled. We're all happy because we're flying across the wind. So we've got no wind component. 65 knots, all good. Our integrator's running. We've reached our trim values. Everything's flying nicely. Then we turn to line up for our final approach. Now, as we turn, suddenly we've got this 30-knot headwind. Our airspeed is still 65 knots, but our ground speed is now going to be 35 knots. Our integrator is going to disable itself, and all of a sudden all our nice trim values that our integrators have accumulated will go away. Particularly if we're in high winds, we probably don't want things like our heading hold to lose their integral control. We probably don't want our pitch to lose its integrator value whilst we're still in the air. So there's not necessarily a right answer here. Both airspeed and ground speed have pros and cons. There's other things we can use to determine whether we're on the ground. Full-size aircraft will often have a weight on wheels sensor that tells them whether there's weight on the landing gear or not, and they use that to decide whether they're still on the runway or not. Maybe you can use that in conjunction with an airspeed to decide whether you're on the runway or not. I say there's no right answer. What I'm trying to highlight though is that it's important that you think through thoroughly why you're selecting the particular variables that you are, and to really think through these criteria where you enable and disable things, because as we saw earlier with our King Air and its strange pitch up behavior, stuff that we implement with good intentions that works really well when we're close to a set point can behave really weirdly once we get a long way from our ideal conditions, or if we're in situations like on the ground where the aircraft's unable to move. So having said all that, let's take a look at this and see what it actually does to our system, and just see if it does roughly what we want. And if it looks like something we want, maybe we can run with that and we can refine it later, or we can add more additional conditions to when we enable that integrator. And so we got our aircraft sitting on the runway. We have heading hold enabled. We'll set our airspeed set point. We'll set pitch for, say, 5 degrees, and we'll enable our integrator, and nothing happens, and that's our intended behavior. Right? So whereas if on the other hand we were to go and look at airspeed, where I haven't made that modification to the integral, and we were to enable the integral here, we'll see it will start winding up like we would expect. Okay, so let's let that go, and what we should see, or what we expect to see, is that as we hit 40 knots, the integral should be enabled and the system should start behaving how we want. So let's see if that happens. It's 40 knots there, and we can see that our integral's been enabled, and off it goes. So in this particular situation, that looks like it works pretty well, but I just want to emphasize again, there's a lot of different combinations of conditions that our aircraft can experience, and it might not work for all of them. And that's one of the reasons why simulation tools like this are so valuable, because I can sit here and I can play with 1,000 different situations, and I'm never going to damage an aircraft, I'm not going to burn any fuel, I don't even have to go outside if the weather's horrible. You know, I can have whatever wind I want, everything I want, and I can find all those corner cases and those niche conditions where the controller's not going to do what I intended it to do. So another problem that you might come across, and we haven't really seen it yet, but we will see it later. So imagine that instead of being a pitch controller, that this is an altitude controller, which is something we'll look at in a few videos time. And so we can set our altitude anywhere from ground level to 30,000 feet. We've got an integral term, just like we have on our pitch controller, that makes sure that we get to the altitude we want to get to. Now, at the moment, I've set our set point to 2,500 feet, maybe a nice pattern altitude. And if we enable our integral term, it goes up at a certain rate. And so obviously that's winding up, and it's going to have the effect both of winding up the integrator and also producing overshoot when we get to our desired set point. Now the big problem that we've got with this though is that if I just do that again and you look at that rate that goes up, you know, it increases quite rapidly. But if I was to now say set my set point to 15,000 feet, you can see that our integral goes up far more sharply. And if I repeat the same thing again, say I'm sitting on the ground and I want to climb out and climb all the way to 30,000 feet, and I don't want to have any involvement, I just want to turn it on and go, and I turn that on now, you can see that it shoots through the roof. So the situation that we've got here is that we have a system that has a very large range of set points, and I guess you could say that it has a high dynamic range. So the values that we might want to set could be anywhere from 0 to 30,000, but we would still like to have control probably down to within sort of at least 10 feet, possibly better than that. So we need to have enough gain that we have the fine control that we need, but then the downside to that is that when that gets multiplied by a very, very large error value, both our proportional value will be huge, but also our integral will be large and will grow very rapidly. And with something like an altitude controller, we don't really want it to behave differently whether we've set it to 2,500 feet or 30,000 feet. We would probably expect our system to have a more aggressive response if the error value is, say, 10,000 feet than if it's 10 feet. But we probably don't want it to behave differently if the error is 10,000 feet or 30,000 feet. And we probably don't even want it to behave differently if it's 10,000 feet or 1,000 feet. The reality is that most of the aircraft that we're controlling are only going to have unlimited climbing performance anyway. They're only going to be able to climb at so many feet per minute. And so you don't want a 30,000 foot set point to make the aircraft try and climb 10 times as hard as a 3,000 foot set point error. So we want it to sort of, above some amount, we want it to behave pretty much the same. Now, there's a few ways we can do this, but if we've just got a single control loop like this, one of the ways that we could do that is just by capping the error value. So we could say, regardless of what size our set point error is, we're going to cap the error so that it looks like it's only ever a 1,000 foot error. You also tend to see this behavior for heading control loops, because that's another loop where we have a reasonably large dynamic range, if that's what we want to call it, where, you know, we probably want to be able to control our heading accurately to within a degree or two, but our error can be anywhere up to 180 degrees. So we've got two orders of magnitude of range in the error that we're looking at, And again, we probably don't want the aircraft to behave much differently for a 180 degree heading error as we would for, say, a 30 degree heading error. So above some amount of heading error, we could just cap that error value to, say, 30 degrees. The way that we would go about limiting the magnitude of our error value is we can just use one of these in-range or coerce blocks. And I've actually got another video separate to this where I describe a bit about what they do, but basically they just take an input value and they cap it to be within a range. So if the value is within that range, it passes straight through, otherwise it gets capped. And so it takes two inputs, which is an upper limit and a lower limit. In this case, I'm just feeding in one number as the upper limit and the negative of that number as the lower limit. So I'm saying that my error value is going to be capped to within plus or minus 2.5. In this case, because we're discussing integral windup, I've only applied this error limiting to our integral term, or to the error where it goes into our integral. However, in other situations, possibly such as the ones I discussed before with heading and altitude control, you may want to perform this limiting, if you're going to do it, on the error before it feeds into any of the terms. So at the moment, how I've configured it, our proportional term is completely unaffected, and it's only our integral term that's affected. But if we were to move this block here, all these elements, up into prior to this junction here, we would also affect the proportional term and later on the derivative term when we've got it. Now again, you need to think about what you're trying to achieve and think carefully about what effects this is going to have before you decide when and where you want to do this. So let's have a look at what it does to the integral term for our normal pitch controller that we had before. Okay, let's have a look at what this actually does. Our aircraft sitting on the runway, as always. We've got our controller set up all the same gains as normal. At the moment I've got our pitch set point just set to 2.5 degrees because that's the pitch that the Cessna sits at when it's sitting on the runway, and our integral is not enabled. So what we're doing is we're limiting our error values to be within plus or minus 2.5 degrees. So the graph on the right hand side is showing the true error rather than the capped error, so it still has the full range that we would expect. What we should see now though is that when we enable the integral, if we were to go up to 5 degrees, we'll see it go up at a certain rate, and that's good. What we'll find though is that if we go have a large error, the integral will still increase at exactly the same rate as before. So I've just switched back to our previous system to demonstrate what the existing behavior was. So I've configured this to input a triangle wave in pitch, and we're going to watch how the integral follows that triangle wave. So this is our triangle wave. So our error increases linearly up to a maximum, then decreases linearly down to a minimum. And what we'll see when we enable the integral is that it's curved. So as the error gets larger, the rate of increase of the integral gets steeper and steeper. And then as it comes back the other way, the integral flattens off and follows it. So what you've got is like this lagging sinusoid that follows the triangle, and so you can see the sort of scale of it as well, or from about minus 900 up to about plus 600, so a range of about 1500. So let's go look at the new system. What we see in our new system when we do the same thing is we enable our integral, we insert our triangle wave, and we'll see that the integral is basically linear. It has these rounded points to it, and that's the area where the error is below 2.5 degrees. But everywhere else, the rate of change of the integral is effectively capped because we've limited the error value itself. So hopefully it should be apparent just from the shape of this graph that what we've done is we've slowed down the rate at which the integral is accumulating and the magnitude of the integral, and therefore we've reduced the effectiveness of our integral term. So it's going to respond slower because we've limited the rate at which it can rise, and its ultimate magnitude is less, so the total amount of control power that it has is less. So it's similar but not the same as if we just reduced the integral gain. The difference being that if we reduce the integral gain, that would be linear across the whole range of errors, whereas what we've done here is effectively introduced a non-linearity into the integral term. So those non-linearities are not ideal from an analysis point of view, trying to analyze it mathematically, but they're not necessarily a big deal from a practical sense. But again, you need to assess what effect that's going to have for your particular system, and the simulator here is the way to do that. And I should point out here, if in case it's not obvious, what we've done here does not eliminate integral windup. All it's going to do is reduce how quickly the integral winds up. So in that sense, it's very much the same as just having reduced the integral gain. So if we're looking for a solution to completely eliminate windup, this is not going to be it. But it may be something that helps us reduce windup in certain cases. If you recall back to the video of the C-130 accidentally taking off while taxiing down the runway earlier, one of the things I mentioned was that the output component due to the integral term was up around 1500, and our normal control range is only between plus or minus 1, and so the integral completely dominates the control outputs. So it would almost not matter at all what our proportional term was or our derivative term if we had one. That integral with such a huge value is going to dominate everything. So you might be tempted, having seen that, to go, well, the problem is that the integral is able to exert too much control, and we should limit how much control output the integral is allowed to have. So let's try and do that and then see what effect that might have. In the block diagram here, what I've done, I got rid of the stuff we had before. We're back to feeding in just our straight error value. And what I've done is down here, this is where we calculate our integral term, and then here is where we multiply it by our integral gain. And so what we have coming out of that is effectively our integral output component. And what I've done is I've used another one of these in-range or coerce blocks to limit that value to be within plus or minus 1. Now, plus or minus 1 might not be the range we actually want. Consider the case where our proportional control is generating a large output, say, I don't know, maybe minus 3, because we don't have any limiting on our proportional control. So it can still go to quite large values depending how far away we are from our set point. So if it was at, say, minus 3, but where we needed to be was somewhere much closer to 0, capping this to between plus or minus 1 may not give the integral enough control authority. So maybe we might want to actually be a bit less restrictive and limit this to plus or minus 2 or plus or minus 3 or something. But that's probably something you'd determine experimentally. This should be enough for us to at least see what effect it has. So what I'm going to do I'm going to switch back to our King Air that we had before. I'm going to let it wind up on the runway, and then we're going to try and take off again and see what sort of behavior we get now. Okay, I've let this wind up on the runway, and you can see that our integral's up to quite a large value now. And so previously, at this point, our integral output component, when it's multiplied by that gain, would be 54. So, you know, massively overpowering the little proportional output here that's at 0.5. But now we've capped it. So this red line here is our integral control output at 1, and it doesn't rise above regardless of where our integral goes. And you can see that our total control output is still up here. It's at 1.5, which is going to max out our elevator. So we're still going to try and take off with max elevator. It's still not going to be perfect, but let's see what it does. Now, if you remember previously when we tried to take off in the King Air, it would pitch up to almost vertical, and then it would stall, and then it would come back down, and it would just repeat that cycle. Let's see if this behaves any better. See if our proportional control is able to interact a bit better and have some control authority. So you can see here our proportional control comes down, and it's basically got enough power that it can fight against our integral term, even though our integral term is still maxed out, and our total control output is down here, and it's a reasonable value. And as you can see, the aircraft took off very smoothly. So this doesn't eliminate the wind-up problem as such. Like, the wind-up is still there, but we've limited how much effect it can have on the system. What you should note too is that even though our set point is 5 degrees, the combination of all these control outputs has us sitting at just over 12 degrees of pitch. So the system doesn't work perfectly, and if we were to try and hold -5 degrees, because our integral output is still here and our total control output is still going to be positive, we're still going to maintain positive 3 degrees of pitch at the moment, even though we're trying to get to -5. So the system, it doesn't work how we'd want it to work, but it's much more controllable and much more stable and much less likely to result in some sort of unplanned disaster than the system that we had before. So that got us some of our controllability back, but it didn't eliminate the wind-up problem for us. So what can we do to try and get rid of the wind-up whilst maintaining what we'd achieved just then? What we can do is we can still limit the integral control output, but rather than limiting it on the output side, we'll limit it on the integral side. So let me show you what I'm talking about. Okay, so previously we were limiting the control output, so after the integral had been multiplied by the integral gain, we were limiting it to being between plus or minus 1. So that meant that the integral itself could still grow or shrink to any size it wanted without bounds, and so you still had that time varying aspect where, depending on how long the aircraft had been sitting on the ground, would determine how much wind up you had, how long it would take to unwind, all those sorts of things. What we're doing now is we're still limiting that control output, but we're limiting it by limiting how large the interval can grow. So the way that I've done that is we've still got this coercive in range block. I've still negating my positive value to get my negative value, but now where I'm getting that value from is I'm taking what I would like my maximum integral output component to be, and I've kept it at 1 to make it similar to the last example we looked at, and I'm dividing that by our gain. So that'll give us whatever, we don't really care what the actual number is that's in the integral, but that'll calculate what that number should be such that our output integral component is limited to 1. So in this case, the numbers are pretty basic. So our gain that we've been using forever is 0.001, and we want a maximum output of 1. So the integral that's going to give us that when multiplied by that gain is 1000. But the advantage of doing this is that I can change this value if I decide I want more or less control output, and I can change the gain in real time while the system's running, and this will recalculate what the limits on that integral should be. So let's have a look at how that performs. Okay, same situation as before, aircraft sitting on the ground. I set my pitch set point to 5 degrees and I enable my integral. My integral component will grow. My integral up here is growing, and what we see is it gets to 1000 and it stops, and our integral component here is capped to exactly 1. Now when we take off initially, so this looks now like what we had in the last example. We've got our total output is a bit over, sort of 1.5, proportional down here. It all looks the same. The difference is this integral is not growing, it's just sitting there at 1000, and so we've stopped our wind up. The system is not winding up, it's not going to get any more wound up than what it is now. So there's no, I could leave it sit here for as long as I want, but there's no point, nothing's going to change. Okay, let's take off and see what happens. So we can see that our system, whilst it started off the same as the last example, because that integral was capped, it's come down very quickly towards what its steady state value is actually going to be. So the takeoff wasn't perfect, there was some oscillation there, but we're hardly even down off the ground, and we're sitting exactly at our, we're within 0.1 of a degree of our desired pitch angle, and that, within 0.02 of a degree now of our desired pitch angle, and the system from now on will continue to behave as it was before. So we shouldn't get significant wind up. Let's do that one more time and just keep an eye on the pitch response and just see what it looks like. So it's not perfect, but that's a pretty nice takeoff, all things considered. And I think we could probably avoid some of that oscillation just by having a lower pitch set point to start with. So some of the advantages of this particular method is because we're not limiting how fast the integral can accumulate, we're not affecting the response speed of the system. The system will still respond as quickly as it did before, So unlike the previous solution where it was kind of similar to reducing gain, this doesn't have that effect. The other thing that this does is it removes the possibility of overflowing our variables, which is something that I'm going to talk about in a separate video, but it's a significant and very real issue, particularly when implementing control systems on microcontrollers that have smaller width variables, smaller words. If you're working with an 8-bit or a 16-bit system, it can be a very real thing. I mean, it's still a real thing here, and we can demonstrate it, and we will demonstrate it with X-Plane and LabVIEW on a PC, but it's more of a big deal on microcontrollers, and so that's something that we need to be aware of. But this particular solution basically ensures that we won't overflow the variable that we're using to store our integral. So much for shorter videos, eh? I hope you enjoyed this video. In the next video, we'll look at variable overflow and how it affects real-world systems. If you have any questions, comments or feedback, please post in the comments section below. And if you found this video interesting or informative and would like to see more videos like it in future, please like and subscribe.